Hello everyone, today we want to do an example on the heat exchangers. So we have on R134A to be cooled by water in a condenser. You can see on the right picture, water is entering the heat exchanger with a temperature of 15 degrees Celsius and leaving the system with a temperature of 25 degrees Celsius, and R134A entering with 70 degrees Celsius and living at basically 35 degrees Celsius. So basically we are cooling down the R134 and we are neglecting the pressure drop, and we are asked to calculate basically the mass flow rate of the cooling water. So the purpose of the first part of this problem is to calculate the m dot, right? So if you write the energy balance equation, if you ignore the heat basically transfer, and so one thing which is important to notice is we do have heat transfer within our system, but we don't have any heat transfer with the surroundings. So if this is your heat exchanger, that you have basically inlet, outlet, that's for R134, inlet, outlet for water, there is gonna be heat transfer within your system. But if you choose your system as the whole heat exchanger, there is no heat transfer with the outside. So Q net is 0 if you consider your system to be the whole heat exchanger. Now if you consider your system to be only the, for example, R134A pipe, then there is going to be heat transfer, and you need to consider that heat transfer. But now that we are considering the whole system, and that whole heat exchanger system is insulated, so there is no heat transfer with the outside. Okay, so this is very important to consider. What system do you choose? Okay, so let me delete this hopefully, and solve this problem. All right, so we need to write the conservation of energy. So there is no heat transfer, as I just mentioned. So Q is 0, right? Sorry for my handwriting. This is not. All right, so Q is 0, right? And that's the Q net, right? And W dot, or work, is also 0. I don't know why is it writing like this. All right, anyway, so we have this, right? And so what do we need to do? It's basically m dot h1 plus m dot h2 plus, is equal to m dot. So one thing that I made a mistake here is that this is not H2, right? This is H3. So these are all entrants. So this is m.1, m.3, H3. And then what is exiting from your system is basically 2 and 4. So m.2 H2 plus m.4 H4, right? So so we have this, right? That's the conservation of energy. But if you look at your system, you can see that the water is coming in, water going out. So from the system, you can say that m.1 is equal to m.2, and m.3 is equal to also m.4, because this is for R134A. This is for water, so they have the same rate coming in and going out, right? So we have this basically system. So if you substitute and within your equation, you can get basically m dot water h1 minus h2 is equal to m dot R134A h4 minus h3, right? So that's one equation, and we have basically this conservation of energy, right? So what we need to do is basically to determine the enthalpies at all these 4 states, And we are also given the mass flow rate of refrigerant, which is 6 kilogram per minute in the problem, right? So we have basically m dot r given to us, right? What we need to find is m dot w, and we need to find all these h values from the tables, right? So I don't think you guys have any issues finding these numbers. For example, we can find one of these numbers. So we have basically water, right, coming in at 15 degrees Celsius, 300 kilopascal, right? And it's a compressed liquid at that state, and you have to go basically to the compressed liquid system and find the enthalpies, right? So this is, for example, table A4, right? If we go to remember, we don't have a compressed liquid table in the book, right? So we have to use basically an estimation of saturated water, saturated mixture table to be able to basically calculate these properties, right? So table A4, if you go to 15 degrees Celsius, right? This is table A4, 15 degrees Celsius. And if you look at basically your HF, that's basically liquid, that number 62.982, that is an estimation of the enthalpy of a compressed liquid. So we'll use that number. The same way you can calculate for all basically other temperatures. For example, the other temperature is 25 degrees Celsius. So if you go to 25, you find HF, you get 104.83 because water is basically in liquid phase. So you can estimate the compressed liquid basically enthalpy using the saturated vapor liquid table mixture. All right, so 134A, the same way you can do basically these calculations and find these enthalpies. So the next thing is basically to put the numbers in. So once you found all the enthalpies, you put the numbers in. H1 is gonna be, just to make sure you guys, once you found it, make sure your numbers are correct. So 62.982 kilojoule per kilogram, that would be H1. H2 will be 104. We found these numbers from the table. I just showed you how to do that. You can do the same thing for R134A. Please remember, at this temperature and pressure, R134A is in superheated vapor entering, and when it leaves the system, the temperature drops significantly, and you will be in compressed liquid phase. So H3 will be 303.87, and H4, that's kilojoule per kilogram, and H4 is going to be 100.88 kilojoule per kilogram. Okay, so once you found all these numbers, you substitute in the energy balance equation, and you can find m dot w to be equal 29.1 kilogram per minute. Okay, so just put the number and make sure you get the same number. The second part of the question is the heat transfer rate from the refrigerant to water. Now look at this. Remember, I just mentioned that if you consider your whole system as basically your control volume, there is no heat exchange with the surrounding. But if you consider just the R134A pipe, then there is a heat transfer between R134A and water, right? So if you consider that, then your system would be different, right? So let's look at this picture. This is what's going to happen. This is going to be your R134A. And that pipe is considered to be your system. And there is a heat exchange between R134A and water, right? So you can write basically the energy balance equation. E dot in minus E dot out is basically, since this is a steady state problem, then the rate is 0. So E dot in is E dot out. What is coming in and what is going out? So basically the heat is going out to the water, right? And basically water is receiving some heat, right? And that's what we want to calculate, right? So let's write the equation. Q dot W, that is basically receiving, is M dot W multiplied by H2 minus H1. That's the equation which is derived here as well. We already found 29.1 for the water. And the difference between enthalpies is basically, sorry, this pen is not working correctly. (29.1) 104.83 minus 62.982. If you multiply these numbers, 1200 18 kilojoule per minute, right? So this is what you're gonna get. So make sure when you want to calculate the heat transfer between these two systems, then you have to isolate one of these systems, either R134A or the water, right? In this case, we wrote the equation for water. You can write the same equation exactly for R134A and get exactly the same number, right? So it doesn't matter which system you choose, the R134A pipe or you choose basically the water pipe. Either one is okay. You get the same results, okay? But you have to write you have to use the right equations. All right, so that's it for this video.